Hi guys. All right. So this is your video lecture for chapter 3. Remember, this is the last chapter where there's going to be a different set of notes associated with video versus reading. Okay. Moving on, every chapter hereafter, it will be all in one document. Okay. All right. So this video in this chapter is all about the properties of water, your chapter 3. And so this is just a quick review of what we talked about in the last video about the properties of water molecules and how they behave around each other, right? So the electronegative nature of oxygen means that it hogs the electrons of these hydrogens, pulls it towards it, and so that makes the oxygen overall more negative, and it makes the hydrogen overall more positive. Now, that's a really important characteristic for this water molecule. Why? Because it enables that there to be this weak force between all of the different water molecules, because this slightly negative oxygen is going to have a weak hydrogen bond with the slightly positive hydrogen of another water molecule. Okay. And so again, the reference, I've said it a couple of times, but I think it's a really good visual, right? So if you have one little tiny piece of Velcro, you're not going to be able to stick very much to it, right? It's just one little piece. But if you have a big wall of Velcro and you put on a Velcro suit, you can run up and stick to the Velcro wall, because the addition and combination of all of those little pieces of Velcro make it a really strong, sticky thing, right? We can apply that same thing to water molecules. So combined, hundreds of thousands or trillions of water molecules combined, the combination of these weak hydrogen bonds between them actually makes it overall strong, right? That's why if you belly flop, from experience, it hurts when you belly flop. All right. So that's just a quick review. So this video is going to be all about the unique properties of water. Okay. And so here's a quick list of the properties of water. And so this is all the result of that hydrogen bonding. Okay. So we see that we have a high heat capacity. And basically that means that it can hold a lot of energy. Okay, and then we have high heat of vaporization. Basically, it means it takes a lot of energy before it goes into a phase change. So from liquid to gas, or from solid to liquid. Okay. Next one is that it's a good solvent, not for everything, right? So for example, we could think about if you have ever used Italian dressing, right? So you have to shake it up before you put it on your salad. Why? Because the oil, which is fats, right? They don't mix well with the water molecules in the vinegar, right? So you have to shake them up because of differences in polarity. Okay. Well, and also the fact that the fat is hydrophobic, which we're about to go into later on in the video. Put a pin in it. All right. Okay. So then we have the cohesive and adhesive properties of water. Cohesive meaning that it bonds to itself. Adhesive meaning that it can bind to other surfaces. Okay. And then we have high surface tension. Again, that kind of relates back to the belly flop idea. So you know about surface tension if you've ever belly flopped. And then finally, it's less dense when it's frozen. Okay. So I'm going to show you some slides about that. And why is this so important? Well, because living things are 70 to 90% water, right? So if we are studying biology, study of life, and living things are between 70 and 90% water, then we really need to understand water, right? And we also need to understand how the hydrogen bonds between each other and the cohesion between water and the polar charges between molecules, that's adhesion, all of the different properties, we need to understand them so that we can see what the biological benefits are for living things and how it influences life. Okay. And so just to sort of clarify in terms of your notes, so I have sort of two columns this time that you need to be filling in. So you have on the left column, I'm going to be calling out sort of the definition items, but I'm also having the 6 biological benefits of water, okay? And they're related to each of these properties. Okay, so here we go. First property. Okay, so the first one we're going to be talking about is its high heat capacity. So I'm going to move myself a little bit. I just want you to take a look at this and see what you notice. It's a whole big flurry of color. So what do you notice? So hopefully what popped out to you is that the land is white, right? You can see Australia here in white. So the land surfaces are white. And so all of the bodies of water we're seeing are represented in a color scale to represent surface temperature. Okay, so what are you seeing? Okay, so you're seeing that in the equatorial region, it's much hotter. Okay, there's much more energy at the equator versus the poles. Okay, so when the sunlight hits the surface of Earth, the amount of energy that it takes in, the water on our planet is able to maintain a more normal temperature range on our planet because it has such a high capacity to take in heat. Okay, so, oops, this clicker. Okay, so what is the biological benefit of this high heat capacity? Well, let's relate it to the biological organisms that live on the planet, right? So really it protects living things from these really rapid temperature changes. And because of that, it helps us maintain what? Homeostasis, okay? So if we go to our biological benefits, right? Biological benefits is that it, number one, it protects organisms from rapid temperature changes and helps them maintain homeostasis. Okay, and if you did not catch the first fill in on the left column, living things are 70 to 90% water. All right. Okay. All right, so now we have a new graph we're taking a look at. I want to just give you a moment again, analyze the graph, see what you think it's telling you. It's related to the high heat of vaporization of water, okay? So basically, let's see what this is trying to say. So it's saying for water to go from a solid to a liquid, it requires 80 calories of energy, okay? So for it to go from a liquid to a gas, it requires a ton of energy, 540 calories of energy, okay? So this high heat of vaporization in your notes, okay, it takes a great deal of energy before water will evaporate, okay? The other part of your notes, so we'll go through here. High heat of vaporization takes a great deal of energy before water will evaporate. Hydrogen bonds hold water together as a liquid. Hold the water together as a liquid. Okay, so essentially, because of water's tendency to want to hang on to each other, it requires a lot of calories to pull them away from each other. So I kind of want you to think of like if water molecules are evaporating out of a pot of boiling water, right? So you're seeing when you see the steam, that's water molecules vaporizing. So I want you to kind of think of the water that hasn't vaporized yet. It's kind of clinging on to its brothers that are leaving it, right? Going vapor, trying to hold on and cling on until, well, it lets go and it has vaporized. So for it to do that let go, it takes a lot of energy, 540 calories of energy. Okay. And so if you thought that was the most ridiculous looking thing ever, then that's how I think about boiling water. Now you know. All right. So for your biological benefits for number 2. So why is this high heat of vaporization a positive and a biological benefit? Because it moderates Earth's surface temperature. It permits living systems to exist. Okay, so it moderates the Earth's surface temperature and permits living system to exist. All right. Okay, so what's going on here? All right. So this elephant, it's putting water on its body, okay, and whoever's riding on top of it. And so this helps cool that organism, right? So as we move around, we think of the first law of thermodynamics, right? That energy can never be created nor destroyed. And then the second one is that every time it changes form, you lose some of that as heat, right? So as his muscles move, he's generating heat. Okay, that heat energy will go where there is less energy, right? So it'll go into the water molecules. It can be transferred into the water molecules. And then those water molecules can evaporate, right? And help cool him off. Okay, so let's move on to this. Okay, so these are two words that we definitely need you to have. And I just want to make sure in your notes there's nowhere that I'm skipping for you. So number 3, I gave it to you, right? So we're talking about solvents, okay? That water can be an excellent solvent for things that are hydrophilic. Phil means love. You can think of Philadelphia. It means the city of love. So hydrophilic. So versus hydrophobic. Phobia means fear. So there are molecules that will act differently and engage differently with water based on if they are hydrophilic. They're really great. Water is a great solvent for hydrophilic substances, and it's not a good solvent for hydrophobic substances. Okay. I also just do want to add here. So I want you to think again, we're referring back to if living things are 70 to 90% water, okay? And our cells are made of some substances that are hydrophobic and some that are hydrophilic. Us understanding how water works will help us understand how water will interact with the different molecules in the cells of our body, okay? So I just wanted to give a little bit more biological context. Okay, so here is an example of water as a solvent for hydrophilic molecules, okay? So if you take a look at it, you can see that the water molecules are behaving differently around these ions. So let's see if you see it before I break it down. Okay, so hopefully you noticed for this sodium ion, right, that the oxygen side of the water molecule is what's being arranged towards the sodium ion, right? Versus our chloride ion, we're seeing that the hydrogens on the water molecule are arranging themselves towards the chloride ion, chloride ion. That's a mouthful. Okay, so in this case, right, when salt is dissolved in water, it's got this negative charge, right? So look at the hydrogens that point towards the chlorine, right? So the hydrogens are partially positive, so it's a good solvent for something that has a charge, or if it's a polar molecule where there's a partial charge. So on your notes, I think I gave you everything. For hydrophobic, I explained hydrophilic, okay, and a solvent can have dissolved substances in it, a solute, okay. So if we think about in our body, right, so blood plasmas, we could relate that to blood plasmas and the different charges. Okay, so let's move on to the concept of cohesion and adhesion, all right? So I'm gonna make myself big. I wanna talk to you a little bit about how water moves through a tree, okay? And how really the properties of water are critical to the tree getting what it needs in terms of water from the soil, okay? So you know the source of the water for the tree is the roots, right? So the water comes up the roots, okay? And how does it make it all the way up to the tippy top of the tree, right? So it's telling you something is going on here because the water is moving against gravity. And so how could that be possible? How can we get water to go upward against gravity? All right. Well, the first word you're probably already familiar with is this concept of transpiration. Okay. And essentially, that's the evaporation out of the stomata, the little holes in the leaves. Okay. So, but what happens is that because all of the water molecules have the property of cohesion, where one water molecule wants to cling to itself, okay, because of the polarity, because of the polar nature of water. So, and those weak hydrogen bonds between them. So they are connected to each other that way. But the second part is that there's adhesion going on. So they're going up the tree, right? Partly because of cohesion, because of their clinging to each other, but they are also moving their way from the roots up to the top of the tree because of adhesion, which is the water molecule's ability to adhere or stick to the surfaces around it that are also slightly polar. Okay. In this case, they are adhering to the xylem. Okay, so basically, like in our body, we have arteries, blood vessels. Trees have xylem and phloem. Okay, so the water molecules are sticking to each other, cohesion, and they're sticking to the walls of the xylem and the phloem, and that is starting to help pull them up from the roots up through the tree. Okay, and so and keep in mind though, that's because the xylem and the phloem are polar surfaces too. Okay, so they also are moving due to water pressure. Okay, so we're going to talk a little bit more about that later, but because there's a difference in water potential, that's another reason that will pull them up, the water molecules up the tree. Okay, but let's just simply say that when you have a water molecule that's at the top of the tree and it's gaining energy and it's getting more energy, right? The amount of kilocalories that it takes for it to evaporate, it takes a lot of energy. But when it goes, because it's connected to another water molecule, right, that's trying to pull that one up, it's like this whole chain, right? And that's why you're able to go from water in the roots all the way to transpiration out the leaves, okay? Because the cohesive property of water molecules are trying to cling on to each other. All right. So the other part that's really important about this is that the water in the ground is cool, right? And so this is a really important property as well, because as the water moves through the organism, it's also cooling the plant, okay? So it's bringing cooler water from the soil through the plant. All right. So in your notes, want to make sure I'm more clear with your notes. So cohesive, number 4, cohesive and adhesive, right? Bonds with itself and to other polar surfaces. Okay. So what's the biological benefit of that? So I gave it to you over here. Allows water to move up through trees, transpiration, adhesion, cohesion, and tension. All right. So we haven't really talked about the fourth one yet. Okay. But if we're talking about water potential, anything in terms of potential energy, right? Water wants to go from a higher water potential to a lower water potential. Put a pin in that. Okay. So now let's go on to our next slide. Let me make myself a little small. And this is where we can kind of visualize what I was talking about the clinging nature, right? So let's first do the cohesion part, right? So you can see that that weak force between water molecules, is what's pulling them together. So we're having the water being pulled up from the roots because they're sort of yanking on each other, right? And it's pulling up and up and up and until it evaporates out through the leaves, right? But then because of adhesion between the water molecules and the cellulose xylem wall, so the phloem and the xylem, that is the reason that they're sticking to the walls as they're moving up. Okay, so let's keep moving. All right. Okay, so with surface tension, so it's a really important property of water. You can, again, I'm referring to the belly flop repeatedly, but you can think about surface tension is happening when you belly flop into water. It's also happening here for this water strider. Hopefully you can kind of see there's this like indentation where he's walking on the water, okay? And that is because he's able to do this because surface tension is a property of water. Okay. And so another example of this is if you were to pour a glass of water and overfill it just slightly, it's not just going to pour out immediately. It's actually going to sort of stick up over the rim and kind of hang on right there. And that's surface tension. Okay. And so what's the biological benefit of that? Well, we said the water striders like it. Okay, so next one is all about the density of water, okay? And how ice or frozen water is less dense than liquid water. And you can literally see that in this diagram, right? You can see the density of the liquid. The water molecules are much closer together. It's much more dense versus frozen water is significantly less dense. We can see that there's this lattice structure that takes place. It spaces the water molecules away from each other, right? And so there's this equal distance between each water molecule. It's not like it's random spread. It's an equal lattice, okay? And so what happens is that as water loses energy, right? So as the kinetic energy decreases, right, the hydrogen bonds start to stick to each other, to glue together into this lattice form. So the spaces between them expand, their movement slows down, right? And so what I'm sure everybody has maybe experienced the accidentally forgetting that they put a soda in the freezer phenomenon, right? You come back, what happens? It explodes. Why? Because the liquid water in that soda can, it expanded after it was frozen, right? The molecules of water moved away from each other at an equal distance, and it caused the can to explode. Okay. Another example, if you fill your ice cube tray like halfway full, right, with liquid water, you put it in the freezer, you take it out, and it's almost all the way full. Okay. So we're seeing that this is a really important biological benefit for living things. Why? Well, let me give you an example in terms of organisms that live in a lake. Okay. So we don't get winters here in San Diego, but let's think about let's think about lakes in, say, Michigan, where they have really strong winters. Okay. So if water were able to freeze rapidly, okay, and to not be at a lower density when they're frozen, it would be really, really, really detrimental to organisms that live in bodies of water. So if we think about how water moves, okay, in a lake, the coolest water is on the bottom of the lake. Okay. So that cold water on the bottom of the lake, because it's less dense than the liquid water, it floats up to the top surface of the lake. Okay. And then there's this nice frozen layer on top of the lake that provides this layer of insulation so that the entire lake doesn't become frozen solid, right? So if water did not have this property of being less dense when it's frozen, then essentially what would happen is the cold water that's at the bottom of the lake would just move up until the entire lake was frozen solid. And what would happen to everything that was alive inside of the lake? It would all die. Okay. And so the biological benefit, if we go to our notes number 6, ice acts as an insulation layer on a body of water, protecting the life below. Okay. And then on your left-hand side, frozen water is less dense than liquid water. As water approaches freezing, the hydrogen bonds all become equal distance, expanding, become more uniform. All right. So the very last thing we're going to do here is talk about pH. Okay. So again, I want you to just take a look at our little pH scale here. Okay. You can look at your reference point. Hopefully, neutral pH is 7. Okay. The most basic is 14, pH level 14, and something highly acidic would be pH, between 1 and 0. Okay. Extremely acidic. So what is neutral? Oh, I already said that. 7. Okay. So you can see also here, is human blood acidic, neutral, or basic? Hopefully you're seeing that it is slightly basic. Okay. So what I really want to talk about is the logarithmic nature of changing pH level, okay? So I'm going to give an example. So if you were sitting in my classroom right now, it's about 73 degrees, okay? If I cranked up the air conditioner to 74, you guys wouldn't notice. You wouldn't notice the 1 degree, okay? What if I cranked it up to 84? So I went from 74 to 84. Would you notice? How about when I went from 84 to 94 degrees? Would you notice? Yes. How about if I go from 94 to 104 degrees? You would notice. These are drastic 10 degrees changes. You'd feel it. The same goes for pH. So if we were to start at something that's pH 7, okay? If I go to pH 6, it is 10 times more acidic than pH 7. And what is this acidicness, right? Well, it's concentration of hydrogen ions, okay? Versus if something's more basic, it has a high concentration of hydroxide ions. So hopefully you're seeing what happens if you put these two together. OH and H, hello, H2O. Okay, so pH is all about the concentration, and specifically acidity. It's all about the concentration of hydrogen ions. So every change in acidity is a 10-fold change. So I also don't want you to think, so if I go from a pH 4 to a pH 2, that's a difference in 20 in terms of concentration of hydrogen ions. No, it's logarithmic change. So a change from 4 to 3, it's 10 times more hydrogen ions. And again, from 3 to 2 is another 10 times. So from 4 to 2 is 100 times more acidic. So pH 2 is 100 times more acidic than pH 4. Okay, so on your notes, I want you to have that for an acid, it's when put in water, it releases hydrogen ions. Hydrogen ions, when you put in water, I'm just mixing my brain up. An acid is when you put it in water, it releases hydrogen ions, okay? A base is when put in water, it releases hydroxide ions, okay? So essentially it's a measure of hydrogen ions. That's the pH scale, okay? So low pH has high hydrogen ions, and a high pH has a high concentration of hydroxide ions, okay? So then the other finishing of that sentence. So low pH has high hydrogen ions. Each change in value is 10 times the concentration. 10 times the concentration. Then you have in your notes, 0 to 6 is an acid, 7 is neutral, 8 to 14 is a base. Okay, so now we are going to just really, really quickly talk about acid rain. I'm going to have you guys do a reading about acid rain as well, because essentially what happens is when we as humans create air pollution, okay, what happens is when that pollution rains back down, it changes the pH of rainwater, which is already a little bit acidic. It makes it more acidic. And what happens is that when that water comes down, it can destroy structures. You're seeing the deterioration of this gravestone, but it can also change the pH of soil. And so that's really critical to an environment, okay? Because it can affect how plants absorb nutrients. It can really, really devastate an ecosystem. Okay. So finally, we're going to, and this is the last thing we're going to talk about, we're going to talk about buffers. Okay. So on your notes, okay, a buffer is a chemical or a combination of chemicals that keeps the pH within normal limits. Okay? They work by taking up excess ions. Okay? So what's the biological benefit on that one? So like blood pH, right? Because you're going to have, depending on what you eat, okay, your body is going to have some fluctuations in pH of your blood, okay? But that could be really, really bad for your tissues. So there's buffers that absorb some of those ions, some of those hydrogen ions, okay? And that helps maintain a proper pH in your body. And again, the goal is to maintain homeostasis, okay? So we're going to pin it right there. And I will see you in class, you guys.